This is the hollow working. Okay. So this is the working. That is deformation. So primary the working operation and secondary working operation. Okay. Primary working operation involve taking a solid piece of metal and breaking it down successively into rod materials of various shapes by process of forging, rolling, extrusion, and drawing. Forging, rolling using rollers, and this extrusion, you just pull it using a very, very strong machine to pull this raw material through some shape, through some orifices of the different shapes. Extrusion and drawing. So this is forging, rolling, extrusion, drawing, and they are commonly used. This is the metal deformation mechanisms. The second one involves a further process of the products from primary working into final or semi-final products. And for example, just get these bolts, gears, and sheet metal parts. Right? So this is, and the bolts and gears and will be discussed in the materials in the machine design class. So this is primary working operation and the secondary working operation. So the bulk deformation, these parts may have a relatively small surface area to the volume or to the thickness ratio. That is, for example, hand tools, shafts, and turbine disc. These are called bulk. Bulk means that the technically speaking, bulk information means bulk deformation means that surface area to the volume ratio is small. I mean, volume is big, right? Volume is relatively big. A sheet volume, the surface area to the thickness ratio of the product is much larger. Sheet is very, very thin sheet. So, for example, this kind of this one. I use this one as an example. This is very, very thin, but the surface is huge. So if we want to bend these kind of things, it's called sheet metaling. However, if we want to bend these things, right? If we want to, suppose this is a solid material, if we want to do some work to get some final products from it, that is bulk deformation. And for these kind of things, is the sheet form, because the raw material is very, very thin. So definitely we can intuitively we can see this one will need more energy. So this is see the ratio made is much higher and material is subjected to shape changes by various dyes. They use dyes here. And the thickness this thickness variations are usually not desirable as they can lead to the part failure and during manufacturing. For example, copper caps, aircraft, and fuselage. This is the sheet metal, and also this beverage cans, the Coke, the cans we use. And so that is technically sheet metal. So based on these slides, you should know what is a primary working operation, what is a secondary working operation, and what condition we call bulk deformation, and what condition we call sheet forming. But definitely this is kind of relative word, not a very, very strict demarcation line between them. So here is the commonly see the bulk deformation process. Forging and rolling we have flat and shape, flat shape, and extrusion, and drawing and switching. So here is the forging is the oldest one. This is the oldest form of people, humans, ancestors have used this one. So this is the forging and rolling. We have different rollers and put the material inside, and then just let these rollers run, and we can get this is the we can roll the material. Extrusion. Okay, this extrusion and just the production of long lengths of solid or hollow products with constant cross-sectional area, usually performed at elevated temperature. Why? Can somebody tell me why we do this one at elevated temperature? If we elevate the temperature, what will happen? And the material will become softer, right? And so it is much easier to deform it. So this you know that. The drawing is production of long rod, very long, and the tooling with round or various cross sections. So you can take a look at these slides. This is too much details here. But what I want you to know is that bottom line is that you know this basic. This is a block deformation process. Forging and rolling. Rolling contains two. Rolling has two categories: flat and shape. And then the third one is extrusion, drawing, and switching. And switching is visual forging of the discrete or long parts with various internal and external shapes, generally carried out at room temperature and low to moderate office skills. So this is we have so many bulk deformation processes. So forging, we talk about first one is the forging. So forging denotes a family of processes to make the discrete parts, not continuously, discrete parts, in which plastic deformation takes place by compressive forces applied through various dies and tooling. Have you ever seen the forging process? You see? Okay, when I was young in China, when I was young, this 30, 40 years ago. Oh my God, I'm so old now. Okay, so this is on the street, okay, on the street side, and people do these kind of things. So this is some final products, and they want to have better properties. For example, the fatigue life. Okay, at that time, because I was a young boy, I don't know what they are doing, but I don't know what the purpose they are doing that, but I know what they are doing there. And so adding the temperature and then do some work there. And that is the forging. As I said, this one humans ancestors have been using this one many years ago. Right? So it's a plastic deformation. What they want to do is they want to have plastic deformation for this is the raw material and to get the final product of the final shape. So this is called forging. So forging can be carried out at room temperature. So this is cold working. Cold working usually needs more energy, needs more skills. Or at elevated temperatures, this here we call warm or hot, the hot forging. So you can see cold working is less than 0.3 and hot working is greater than 0.6. There's warm working, and so they just have this intermediate disease level. But in the machine design, I told my students we totally have two categories. One is a cold working, one is a hot working. Okay. For that classification, the demarcation line is here. What did I teach you in the machine design? What is the demarcation line for the hot working and the cold working? Recrystallization temperature, right? You understand? Recrystallization temperature of the material. That is the demarcation line for cold working, hot working, and cold working. But in this book, this textbook, the authors are more meticulous, are more dedicated. They just give us three categories. They're totally fine, okay? So this is T. This is the melting temperature. Right? This is 3. We have 3 here. But you need to know this Tm is melting temperature. Melting temperature is not the recrystallization temperature. You be very careful. Right? So this is for this textbook. If I ask you how can we categorize this is working, this is the working categories. You need to tell cold, warm, and hot working. Or you use another one. I said cold working and hot working, and the demarcation line is recrystallization temperature. But here, Tm is the melting temperature. Tm is different from the recrystallization temperature. Okay? Okay, great. This is for forging. And then here is the open die forging. And why is it called open die forging? I have die 1, die 2, right? Why is it called open? Because this workpiece is not raised. if these two dies go together relatively, so the workpiece will be the dimension in this direction will be decreased. However, this guy will expand linearly, right? You agree? So that's the reason this guy is called open die project. So here, this is original D0, original diameter, original height. After I plan load, after some time, I have D1, H1. Further, I have D2, H2. So here, can you see the difference between this one and this one? The difference between this one is that for this one, we just neglect the friction between this surface on this die and the top surface of this is the blank of this workpiece. However, if we take a look at if there we just assume there is a friction, it will have this effect. We call this kind of this bearing. We'll call this bearing. This is another concept I want you to know. Okay, so net shift manufacturing, as the name suggests, net shift manufacturing. Can you tell me without looking at this explanation? Net shift. Let's look at the name. See, the parts produced are as close to the final desired dimensions, tolerance, and specification as possible. So this is called net shift manufacturing. Net shift manufacturing means that you do not need too much post-processing, and then you can save a lot of money. What we call net shift manufacturing. What does net mean in the English language? Suppose I say for the mass net weight is 185 pounds. What does that mean? I mean, that's an effective weight, right? So this is effective shift. Questions? Okay, then this is if we take a look at this is the dying, this is the metal forming process, and then we have the green flow. If we use the microscope to look, so you can see because the barreling, we can have this kind of the deformation. So the green flow lines in our setting a solid, still cylindrical specimen at elevated temperature are between two flat, the cool dies, lower one and upper one. And know that the highly inhomogeneous deformation and the barreling, highly inhomogeneous, this is inhomogeneous. And the difference in shape of the bottom and top solid. Bottom and top is different. This is this shape, and they are different. The lower die before deformation proceeds. So the latter results from the hot specimen resting on the lower die before deformation proceeds. The lower portion of the specimen begin to cool, thus exhibiting higher strength and hence deform less on the top surface. So this is from the this professor. And then if we can just use schematic illustration. So here is the grains here. Okay, this grains here. And we compress it, and then we have this one. The thickness becomes lower, but it's expanded this way. But because of friction, we will have this barreling phenomenon here. So for our problem, for our homework number 2, and we will just use the room temperature. We will not use the elevated temperature. However, if you are curious, and you can change the operating temperature and to see how it works. Okay? But I give you this flexibility if you want to elevate the temperature to suppose 200 degrees C, and you can see how different it is when you deform the workpiece at room temperature. So then we do some. This is a calculation, slab analysis. This is of volume. So here, if we look at this is a part. This is one die. This is upper die. This is a lower die. We have this is this is a workpiece, okay? And suppose this is x, suppose this is dx. Dx is an infinitesimally small one, dx. So this is h1. So we just take this dx or this slice out of here, right? Or this slice out, and we know that on this side we have sigma x, on this side we have sigma y. The sigma, I'm sorry, sigma x, this is sigma x plus d sigma x. Do you agree? Are you taking the CAE class now? Justin, are you taking the CAE computer aided engineering class now?
They take it next semester.
Oh, next semester?
No, next next semester.
Okay. So who have already taken the CAE class? Okay. Who have taken mechanics of solids?
Taking mechanics of solids. I'm in.
So who is teaching?
Dylan.
Huh? Yeah, who is teaching?
Oh,
Okay.
who's teaching? Which one?
Mechanics of solids.
I'm not. I took that last semester.
Oh, okay. So
I'm in CAE with Dr. Lay.
okay. Okay, great. Thank you for the information. So I have never taught mechanical solids, but in the CAE, I taught my students how to do this kind of analysis. Okay, so this is sigma x, and this is sigma x plus d sigma x. Why? Because there is a difference. The sigma is different. So here I have sigma y, right? This is the sigma y. This is sigma y, sigma y here, sigma y here. But there is a mu here. Okay, so there is a mu. Mu is a friction. This is a friction. But this guy is in the state of equilibrium. If this guy is in the state of equilibrium, they can use this equation to get. Okay, how to get this one? Sigma x here. Sigma x plus d sigma x multiplied by h. H is the height. And the thickness, well, because the thickness, actually, this is the stress multiplied by area equals force, right? Do you agree? We only have the force, we only have force balance equation. We do not have stress balance equation. And be very, very careful. Actually, this guy multiplied by h, also multiplied by thickness, h height by thickness is a cross-section area. And this guy multiplied by cross-section area equals the force, right? But because here is a t thickness, and here is a t also, and here is a t also. So the t is then 0, and it just cancel the t. You understand, okay? So here, are you okay? Okay, so as I said, okay, we only have force balance equation. We do not have the stress balance equation. The force in this direction, here, this is a stress multiplied by the area equals force, right? Stress is defined as the force per unit area. So the stress multiplied by corresponding area equals the force. So this one multiplied by h multiplied by t equals the force on this side. And plus 2 mu. Why is it 2 mu? There is 1 and there is 1. 2 mu sigma y, 2 mu sigma y is a stress dx. This is a dx in this direction, dx. And then multiplied by the thickness, right? The thickness. Dx multiplied by thickness is the area on the top. The stress multiplied by area on top is the force. And the same thing for this one. Then we have this one equals 0. This one, then we further down, we can get this. Sigma x equals sigma y minus y prime. Y prime is the Euler strength. Multiplied by this. So this one is analytical solution, okay? If you are interested, you can use the abacus to calculate. definitely you can use Abacus to visualize the results after you finish the modeling. So the die pressure. So here is the distribution of the die pressure when you compress it in dimensionless form of Py. The pressure divided by y prime. Y prime is the yield strength. Yield strength. This should be yield strength. Okay. Actually, I disagree with here. I'm not okay with here. This should be yield strength. Strength is a material property. Stress is dependent upon your loading condition. But some researchers they just interchangeably use them. But I'm totally fine. But we should be very careful. Question? So here is it. Well, do you have any question? Okay. So here is the distribution. Okay? In the middle is the highest one. And y prime is the yield strength, the material parameter. This is a material parameter. And P is the pressure. Because the pressure and yield strength they have the same units, so the ratio of them will become dimensionless. So here is the die pressure distribution in compressing a rectangular workpiece with threading friction. If we have threading friction and the pressure distribution and looks this way. And for our, here is a plane strain compression. And do you have idea what is a plane strain mean? Plane strain and plane stress. First, they are 2D, right? They are 2D simplification for the 3D problem. Let me write down. On the plane stress and the plane strain. So here, this is a thin plate. And so this plane strain is a thick plate. So both of them are treated as 2D. So they are the simplification of 3D problems. So they are 2D problems. Actually, they are 2D problems. Plane strain and plane stress. So here, so this is increase in die workpiece contact area of original rectangular section. So here is the original cross-section area, this one. So this is of the first reduction. So this is of the second reduction when you compress the workpiece continuously. So the slab methods for cylindrical workpiece, for cylindrical, if the workpiece of the cylindrical, because of the symmetry, we can just use this part, okay? Use this one. We can just use the slice, just as the pizza slice. Just because the cylindrical, we can just use the slice and to get. For this one, we do the free body diagram, and we also know that. So this one, this is the dark volume is in the state of equilibrium here. So we can just use the force balance equations, okay? And then we can get this one, P equals Y. Y is here also. Y is the yield strength of the material. So this is average pressure can be calculated using this one, and 14 force can be calculated and using this equation. The die pressure. So this is you can see the ratio of average die pressure and to yield strength. And as I said, I would suggest to use yield strength instead of stress as a function of friction and aspect ratio of the specimen. Aspect ratio is the height. Aspect ratio means the ratio of the height and the dimension, or the in-plane dimension. Right? You have sense? For example, if this is my workpiece, it is aspect ratio is very, very high. Why I call that? Because the dimension in this plane is much bigger than the dimension in another direction. So this is called high aspect ratio specimen. So this A is the plane string compression, and B is the compression of solid cylindrical specimen. It's just a different mu. So you can see different frictional coefficient, and you will have different the curves. And we're sticking condition, sticking this P over Y prime. I don't know why this guy use sometimes use Y prime, sometimes use Y. Okay, but we should know they are the same. They are the yield strength. The results for sticking friction in plane and for cylinder, and you use this different equations. So Y prime is for the plane strain. This Y here they use for cylinder, but for material, for bulk material, and it should be the same. So this is a finite element analysis. Just the author shows here. This is finite element analysis. So here this is workpiece, upper die, and lower die. And for our problem, we just have for the 2D. Okay, we just have a 2D, and we have workpiece, and also we fix the bottom line. We use to fix the bottom, but on the top we use a die. We use a rigid plate, and to standard for to mimic the die. So we are going to do this one. Do this. Not exactly the same, but here it is a cylindrical specimen. But we will do a square. It's a 2D problem. So this step pressure and aspect ratio. So the plane string examples. So here is this is height h. So here, okay, you just draw it. This is the plastic deformation in plane string. So this is the high H over L ratio. This is indenting with flat die. So this is flat die. You draw it, okay? This is similar to the caulking process. And another one, the B is the drawing. Is a B. B is a drawing or extrusion of the strip with wedge-shaped die. This shape. The die is wedge shaped. So here is original diameter or the height, and then here is a final diameter or the height, and you use very this is a big force to pull it. This is definitely the die. This die here and will be fixed here, and the die will experience a bigger pressure here. The C is also drawing here. So this is L. This is final H0, H1, and this is the original H0, and D is rhodium, and this is iodine. This is the D is rhodium. Rhodium. So here is a roller, and here is a roller, and so we just this is a workpiece just goes through. We can see we have the height reduction, and from H0 and to this is H. The final. So previously, we had in a mechanical engineering lab, and we have this rhodium lab. We have this rhodium lab. Okay? We just have a specimen. We feed the specimen into between two rollers, and then the rollers rotate, and then we can see out. This one is compressed, is processed, and then we see how hard it changes. Because we know that we will introduce is the hard. This is the residual stress. Definitely, finally, the hardness will be much higher than the initial hardness. So here is a type of forging, impression die forging. Right? So here is a die, is a blank. We call it workpiece or call it blank. And so this is another die. And here, see, And we have this mold, look like mold. Yes, this is our final, product, final shape. And here is a flash. Flash means that residual. This is undesired residual. We call it flash. Excessive material that subsequently has to be peeled off. So this is not needed. The forging force equals can be applied, can be calculated using this equation. So see, YF is a flow stress, that's the strain rate and temperature, and to which the material is subject. So I will not test your understanding, but you can just, if there's a need, you can just come back to use it, right? So this is load stroke, the curve. Load stroke is a forging stroke, and how far you go. So here, a die, this is an offsetting, this workpiece is a filling. So this is, this one is a flash. You can see the flash here. So here is the forging stroke, how far you go. And so here is the forging load. And we can see that when the forging completed and the die closed, is here. So this is the forging load, is the heaviest one. The type of forging, we have precision forging and closed die forging, isothermal forging, and incremental forging. We actually have four. This is precision forging. The special dies are made to a higher accuracy. And so this is a closed die. The closed die forging, no flash is formed. It's closed. And isothermal forging, the hollow forging. Isothermal means that the temperature is the same, remains the same. The hollow forging, the dies in the process are heated to the same temperature as the hollow blank. This is called isothermal forging. Incremental forging, the blank is forged into a shape with a specifically designed tooling and die set and form it in several small steps. Where it can be noticed that the die workpiece contact area is small. So we have four different forgings. So we have another orbital forging. So this is orbital, and this is spiral, this is planetary, and this is straight line. So this is a blank. See? This blank is a workpiece. This is a die. You just compress it. So here is a after you finish, and you just remove this die and use the injector and to pull this forged workpiece out. So heading and piercing, and so this is forming the heads of the fasteners. Fasteners, we will talk about these fasteners in machine design class, and such as bolts and rivets. So these are heading processes for bolts and rivets. So here is a piercing operation. So this is workpiece. So here's the die, this punch, and the piercing. Right? So these have piercing. So open die forging. This is two dies, workpiece, and you just pull it, and this goes through. This is the gap between these two dies. So here is the B is reducing the diameter of the bar. You just compress it. And the third one is thickness of rim being reduced by open die forging. So this is rotating. This guy is rotating the workpiece, and you just put the die there and you compress it. And so you want to reduce the diameter of this workpiece. Roll forging. This roller will be continuously moving this workpiece, and we can have different shapes of the rollers, right? And so this one, and so although the B here, this one, workpiece is a roller, different. You can see different shape. Here is a this is a different shape, concave here. Production of ball bearing. Is a ball bearing. We'll talk. It's a very important concept.